and then at that time you will go to the test and test it on the unknown data. Okay, so through this process, you'll be able to fine tune it, come up with the better model. But still, it's more of a art right now, meaning, with experience, you have a feel for, oh, for this data, this should work. It's not a hard, solid science yet. Okay, but people are working to develop that. Okay, anyway, coming back to it, let's say this was the decision boundary given to us, this type of data. We experimented, we said, okay, if we use 50 neurons in the hidden layer, build this model, we feed some training data, we backpropagate, we run it through some epochs. After it learns, then you'll be able to see it does a really good job for unknown data. Will tell us whether it's above the boundary or below the boundary. Okay. So anyway, so let me see if everybody followed this. Okay. What if I have 2 neurons in the hidden layer? What kind of decision boundary will it create? A curve, but a very simple type of curve, right? If we keep increasing the number of neurons, then what kind of decision boundary will it create? More complex, correct? Okay, what if there's a very, very complex decision boundary? Okay, can you still build a neural network so that it will do well on that very difficult, complex boundary? What would you do if you were given that goal? Will you use 5 neurons in the hidden layer or 5 million?
You have to use the second layer.
That's another good point. Perhaps add a second layer, right? So in the 80s, okay, when people were faced with a more complex boundary, this is what they did. You have some inputs. You will create some first hidden layer, let me call it H1. Then they will create another hidden layer, let's call it H2. Then another hidden layer, HN. And then finally the final classification. So they created what we call a deep network. So deep doesn't mean in terms of how many neurons are in the layer. Deep means horizontally that we have more than one layer involved, more than one hidden layer. Okay, so and they were able to learn as complex of a boundary as you can think of. Okay, so people were getting very excited. They were creating deep networks, being able to solve, some biomedical image processing where you're given an image, you have to detect whether somebody has cancer or not, right? Some of these are pretty difficult decision boundaries. So through deep neural networks, they were able to do a great job, and everybody was getting very excited about this until, like I said, one day somebody came up with the mathematical theorem, the universal approximation theorem. So now let me show you what that is. So universal approximation theorem. Okay, so it's you can go home and look up on it. But I'll give you a summary of it. Basically, somebody mathematically proved that to create any complex, no matter how complex that function is, that decision boundary is, okay, all we need is one hidden layer. And again, I'm giving you a very simplistic summary of this. Okay, all we need is one hidden layer with enough neurons. Okay, so mathematically this was proven. Okay, so as soon as the proof came, everybody tossed out neural networks as if they were no use anymore. Okay, why? Because whoever, see, a lot of research at that time was focused in, let's create more complex model with many, many layers. So essentially what this theorem is saying is, no need to create this. All you have to do is pick enough neurons in the hidden layer and it will do exactly the same job as multiple hidden layers are doing for you. Okay? So as soon as, like I said, that theorem came about, and since it's a mathematical proof, what's the need of creating a deep network? So anybody can create a simple network and do the classification and we are done, right? So from literally, from 1990 to almost 2000, I'll say 5 or 2000, maybe 7. Those are called the dark ages of neural networks. Okay, because everybody abandoned them. They went to other classification techniques such as support vector machines, and this basically, everybody lost interest in it, right? Until somebody came up with deep networks which do better than what was thought. So you might say, how is it possible? You know, the theorem says a single network is good enough. Why do we need, right? So very briefly, let me give you the idea. And then I will give you the overview of what kind of things we'll be doing in our course. And then we'll start to dig in more mathematical details. Okay, so the, actually, let me see if I can show it to you. Or actually, let me wait on that. So let me just describe the idea for right now. So the approach that people were following with the neural networks was, so essentially neural network was being used as a classifier. Once again, whether it's a one-class problem, meaning two-class problem, yes-no type of thing, or multi-class problem, is it a tree, is it a frog, or whatever, right? So essentially, neural network was used to learn decision boundaries. Okay, so now there's a couple of possibilities over here. We create a neural network. Okay, regardless, if it's a single class problem, it will have a single output. If it is a 10-class problem, suppose you wanted to recognize 0 through 9 digits, then there will be 10 outputs over here, right? Okay, so the question is, what will we feed it to it? Okay, let's pick this example. Okay, we wanted to be able, the neural network to be able to recognize the handwriting just for digits, meaning is it a digit 5, is it a digit 7, right? Okay, so let's pretend we took, somebody wrote 0, we took a picture of it, we cropped it into 28 by 28 pixels, right? If you multiply 28 by 28, it comes out to 784. Okay, so then a pixel is basically nothing but, if we convert it to grayscale, a value between 0 to 255. So there will be a 784 dots, 28 in each row, 28 in the next row, indicating this is, let's say, the number 0, right? Okay, so then the question is, how do we feed it to a neural network? Suppose you created a network to make a decision between 0 through 9, right? So let's pretend you picked 50 neurons in the hidden layer. Okay, how many neurons will you pick in the output layer? 10, because it's a 10 class problem, right? So you pick 10. If this produces close to a 1, it's a 0. If it produces close to a 1, this digit is a 1, right? So there will be 10 neurons over here. Okay, so now all of these are fully connected, densely connected, correct? So how many inputs will there be to this particular network? Okay, so should we feed in like a matrix like 28 by 28? And the answer is no, because the way the neural networks, standard neural networks work are, they are basically linear array of neurons. So we have to convert this image to a linear array. And how do we do that? We take the first pixel, suppose this is 90. So we'll feed it 90. Suppose we take a look at the second pixel, it's 112, right? We go to the first row, the last number in the first row, let's pretend it's 137. Then we go to the second row. Let's say the first number in the second row is 81. So we basically row by row, we just start, so this is the first row, this is the second row, we start stacking them, and then this is fed as 784 inputs to the network, and then trained, right? Okay, so what's our neural network doing? It's basically looking at the pixels and trying to distinguish whether we can recognize between 0 through 9, right? Will it help us if I created one more hidden layer over here? Will it help us or no? What does the universal approximation theorem say? No, it will not. I could simply, if it's not working, I can simply add more neurons to the hidden layer, right? Okay, so anyway, until around 2000 time frame, somebody came up with the idea of convolutional neural networks. Okay, so I'll just give you a 2-minute idea, then we'll take a break, and then we'll come back and learn some theory. So convolutional neural networks basically are like regular neural networks, but they do some pre-processing. So for the time being, think of it this way. We feed in an image to our neural network. So this is like a pre-processing neural network. In other words, we're not trying to have this pre-processing neural network learn any decision boundary. It's learning what is important in the image. For example, if for a digit, it has to learn that there is some kind of a curve involved. Okay, so we call that features. So this is basically learning features, but not decision boundary. So the first layers of the neural network, we make it learn what is important in an image. For example, if we are doing face recognition, it will learn how does the eye get put together? How does the nose get put together? How does the mouth get put together? So those are what we call features, so that we can distinguish one person from another, right? So no decision being done over here. So how do we make it learn features? Through a concept called convolution. And so I'll go through the mathematical theory of convolution first. And then once you guys understand it, then I'll show you how the neural networks puts it together and is able to learn features. Okay, so typically in a deep convolutional neural network, what we'll do is we'll have several of these convolutional networks. One feeds to another. So here's another convolutional network. Here's another convolutional network. Okay, for the time being, think of it this way. This is one layer. Here's another layer. Here's another layer. But each layer is learning. So this is learning simple curves. Okay. This is learning more complex curves or something. Okay, then this is further. So in case of face recognition, this may be simply learning things like it's curving like this, like on a chin of a person. There's a curvature involved, right? Then this may be further putting it, making it a chin, or making it an eye. Then this may be further putting the eye together so that it can compare two eyes to see if they are similar or not, right? So we put many of these CNN layers, and all of them are learning features. Once they have learned features, for example, how do the eyes, how can an eye in one person can be distinguished from an eye from another person? How can the mouth in one person can be distinguished from the mouth from another person, right? Then we feed it to a classifier. If we wanted to do, let's say, face recognition and recognize who the student is, for example, in this class, if we wanted to create this deep network for face recognition for the 30 students that we have inside this class, how many outputs will we have in our classifier? 30 outputs. Okay. When you create this classifier, if you wanted to use a neural network over here, how many layers will you put over here? One hidden and one output, 2 layers total. Will you put 3 layers over there? Will it give you any benefit? No. Some people do put 3 layers, but perhaps they are not very knowledgeable about the whole theory of neural networks. So a 3-layer, it's not that it will not work. It can do the same job as one hidden layer with enough neurons. Okay. So to summarize, now let me give you an overview of the course. Okay. So first I want to go over standard neural networks. Okay. How backpropagation works. And by the way, there are millions of articles on the internet, video tutorials and so on. But hopefully, the way I will show you, hopefully will be easier to understand. Okay, yes. So I have a different way of learning and teaching. You will, because you have to be totally 100% comfortable with it before we do anything advanced. Okay, so we'll go into complete partial derivatives and the backpropagation. Once you completely understand this, okay, then I will introduce the CNNs. What is convolution? How we make them learn? It has its own interesting, very interesting mathematical theory. And by the way, a lot of people, if you talk to them, they'll say, oh, I program in deep learning, I use TensorFlow. Using TensorFlow, this is literally 3 lines of code to create. But if you ask it, can you create a CNN by yourself? I guarantee you 99.9999% of the world cannot do it. Okay? Even the ones who have gotten PhDs in it, right? Because a lot of them just take it for granted. Oh, you just call the function and it does it for you, right? Like I said, my goal over here is so that some of you are PhD students so that you can go and take it to the next level. Unless you understand the inside of it and you create it. Now, last time I taught this course, I got carried away and I ended up spending 4 weeks on this part alone. So I wouldn't spend as much time, I'll go over the entire mathematical theory, give you my own code so that you can compare it to it, write your own code. For some of the coding, I'll provide my code to you in C#. Sometimes I'll provide it in Python. Okay. Gradually, I would like you to at least have enough knowledge so that you can read and understand C# code. So I won't expect you to program in C#, but because my examples will be in C#, at least you can read. And C# is like Java, like C++. If you know any of those, it's really a piece of cake. Okay, Python, I will give you some tutorials just in case you have not programmed in Python. But Python is extremely easy. For example, I was talking to Professor Lee, whose daughter goes to Stanford, which is one of the top schools. And I was just curious, what do they teach in undergraduates as the first programming language? Okay, for computer science, they're still teaching C++ and some Java, but no Python. Okay. They expect you to be able to pick up Python on your own because, like I said, it's really very, very easy language. Okay, but don't worry, I'll give you some tutorials so that you gradually get better. And in the beginning, I'll even give you some Python code so that you can just slightly change it and gradually get better. But anyway, we'll spend a couple of weeks so that from scratch you can create a CNN on your own. Once you understand how it's done, then we'll take a look at RNNs, which are called recursive neural networks. Okay, see if you take a look at, very briefly, okay, if you take a look at artificial intelligence, right? What exactly is artificial intelligence? Our human behavior you can think of as an example of AI, right? If you take a look at us as humans, we are supposed to be intelligent. How do we accomplish intelligence? Okay. For example, let's take a look at the eye part. What's the job of the eye? To process images, vision, right? Basically, to be able to detect, is this a bird or a plane or a pen or a computer? Then as we are walking, how close are we to something, right? So this is basically doing essentially image recognition. So as you will see, once we create CNNs are great at image recognition. And some of the CNNs have achieved as good of an accuracy as a human being. Okay. Now let's take a look at, for example, our ears. What do our ears do? Voice, right? So part of AI deals with voice. Very similarly, nose is smell, and when we read something, it's natural language processing. So the current state of the art in deep learning is applied to vision. Okay, for example, self-driving cars making decisions where the lanes are and so on, right? Okay, over here at UB we have a separate course, CPEG585. Some of you are already in it. So where we focus more on vision, right? The deep learning itself, excuse me. Okay, also deals with vision. So there's a tiny bit of overlap over here between what we'll do over here in computer vision. But here we will also do natural language processing. We will also focus on where history is involved, like where memory is involved. For example, if let's say stock market is moving this way, right? If we know the history up to this point for a particular stock, how will it behave in the future? So this is where the recursive neural networks come into play, which has some kind of feedback. So after a couple of months, we'll take a look at RNNs. Then we'll also take a look at natural language processing. Then the last part of the course, there are some very exciting topics such as Q-learning, or deep Q-learning. We have what are called adversarial networks. We have what are called adversarial generative networks. With some of the PhD students, I'm very excited about this part. We are working on variational autoencoders. And in my opinion, it has some great future promise over here. And maybe after the break, I'll give you a tiny bit idea of this. So let's take a short break. Then I'll come back and go into some of the theory of it.